All right, everybody, welcome back to the channel. Today, we have a problem in the lab. Our problem is we've been fabricating these devices at JPL that are supposed to pass microwaves through them to the MKIDs. So we call these the feed lines. They're microwave coplanar waveguide transmission lines. And what they have, they have bridges across the top that are designed to keep the ground planes at the same voltage. And there's a silicon nitride pad that's supposed to keep that from shorting. Unfortunately, we're getting shorts. And under the microscope, we saw that these silicon nitride pads are maybe a little smaller than they were supposed to be, and maybe that's what's causing the short. So we are going to try to explosively blow open the shorts. We're going to send in a current through the center strip, and it'll go flow through to the ground. And if there's a short, it should explode it. We can put in amps of current, and the area that we're going through is very small. It's like 2 microns where the shorts have to be. So we'll see how that works. If it does work, we can then try a higher power microwave signal. Maybe we'll put in like 100 milliwatts of like 10 gigahertz RF. And if that works, it might explosively blow open the shorts. Like the microwaves will go until they find a short through it, blow it up, and then they'll keep going to the next one. So it's a nice idea. It almost never works in practice, but we'll give it a try. All right, so first thing we're going to do is measure the current resistance across the feed line. So you can see the device down there in the gold box. Hawkins is now going to hook up the through the these G3PO connectors, which are awfully tiny, and he's going to measure the resistance. So we're measuring center to center pin resistance?
Yep, and there it is.
So we're at 3.6 kilo ohms center to center.
On that feed line, and then on this one.
What's our center to ground resistance?
This one is 800 kilo ohms, or 800 ohms.
Okay, interesting.
Okay, and then let me center to ground. So 500 for the 3.5 kilo ohm feed line. 400 for the 800 ohm, and then 1 second I can.
I think we should blow up from center to ground though, right?
Yes, yeah.
Good.
All right, we're plugging in the power to the high resistance through line. And then I'm just gonna slowly raise the volt. No, it's still there.
Okay, so check the voltage of the source.
Just 10 gigahertz?
Yeah, try 10, sure.
All right, we're at 10.005. Okay, we're at 30.
Bring it back down.
And we're coming down. There it is.
What do we got?
1.6.
So the same?
Yep. No dice.
All right. So do we have a giant amplifier?
Yeah, do we?
All right, 20 volts wasn't enough, so now we've had it hooked up to our 200 volt charge pump for the laser we developed in the last video. You can see that video on the pulse laser at the link above. All right, now we're gonna, not touching it, try to blast it with this.
So I just want to monitor the output to make sure it's not going super unstable. This is not spec'd for a lot of current, so. How bad, what's the short impedance?
3 kilo ohms. On one side, 1.6 on the other. I think we're probably gonna go in the 3 side because it's got an easier contact.
Last time I tried to do this, I just exploded the wire bond, so.
Yeah, that's fine.
Yeah.
That's a reasonable outcome.
All right, someone come here and select the one they want to blow up.
Okay. That looks like a good connection to me. Has this been filmed?
Can I have some glasses?
Yeah. They're right there. No.
No, I expect this to potentially send some metal.
There'll be very...
All right, are we filming right now?
Yeah.
Should I
Go.
turn the lights off?
Let's be quiet and let's film.
Do you want to turn the lights off?
No. Okay, we can turn the lights. I think it'll be right before you hit the button, we'll turn the lights on.
All right, there's no button. I'm just gonna plug this in, so.
I saw a spark.
I saw a spark
I saw a second spark later, too.
I saw a spark on the MKID, not on the,
All right, unplug that thing. Now do it again.
I don't think there's gonna be another spark. I think we popped it.
All right.
I mean, how many more feed lines do we have to go? Yeah, no second spark.
Okay. Yep, another spark. On the MKID or no?
Yeah, on the MKID. And it's now high impedance.
All right, we're trying to measure. We saw sparks on the array, something happened. We're now going to measure center strip to see if we have continuity. If we did, this might actually be worth retesting.
Okay. Center strip to center strip is also broken.
Could be a wire bond that exploded.
Yeah.
Nothing, no center strip to center strip?
Nothing, but let me check the other feed line just to make sure. Yeah, so that one is what I read before. This one is broken. So let's look at it under the microscope. See if we burnt a wire bond or the feed line. All right, so when we looked under the optical microscope, we saw that for the 200 volts, basically every bridge close to the input port had been destroyed. And we realized we were kind of close to the breakdown voltage of the silicon nitride, which is the dielectric that separates the bridge from the feed line. And so we tried again on the second feed line of this device with a 90 volt input. And again, notice the first, 5 or so bridges had all blown. And then there's one a little further away that had blown as well. So it seems like this is effective at blowing some shorted bridges, but only when they're close to the input port. And the other part is that you're going to kill some good bridges as well, because you're just too close to the breakdown voltage of the dielectric. However, this kind of corroborates what we thought was going on with this array, which is that there are some shorted bridges. So we're going to start doing double exposures to make sure that those pads extend all the way out and prevent shorting at the edges. And then we're also going to make that dielectric a bit thicker to avoid the breakdown voltage. Hopefully that solves this problem.